Here we're going to look at 2019 question 10c based on stoichiometry. Okay, so when 3.17 grams of mercury thiocyanate is heated in a well-ventilated fume cupboard, it decomposes completely according to that following reaction. So what mass of C3N4 is produced in this reaction? Okay, so we have the information that we need in order to find the number of moles and so on of our mercury thiocyanate. So we'll just go down here. Alright, so we have the information we need about our mercury thiocyanate. We're trying to find out about this C3N4 over here. Okay, so if we have part 1, okay, our relative mass of that thiocyanate, okay, mercury thiocyanate is 317. The mass we're given in the question is 3.17 grams. So our moles is equal to mass over that relative mass, which is 3.17 grams over 317, which is equal to 0.01 moles. Okay, of our mercury thiocyanate. Okay, if I just go about these, just so it's a bit easier to see. Alright, we see then that 2 moles, okay, that 2 in front of the mercury thiocyanate, 2 moles of that produces 1 mole of your C3N4. Okay, so our ratio is 1:2. So maybe I should write that perhaps as 2:1. Okay, 2 moles of thiocyanate to 1 mole of C3N4. So to get the number of moles of the C3N4, what we're going to do is take our 0.01 moles of thiocyanate, divide that by 2, and then we have 0.005 moles of C3N4. Alright, and that then we are able to use our relative mass then to find the grams of C3N4 that's produced. Okay, so our relative mass of that C3N4 is 92. Multiply that by the number of moles we have, 0.005, and that gives us 0.46 grams. Okay, and that's your answer to part 1. Then, how many litres of oxygen gas measured at standard temperature pressure are required for the complete combustion of CS2? Now, okay, so if we look at our entire formula again, alright, there in that question they're asking us how many litres of oxygen gas measured at standard temperature pressure are required for the complete combustion of CS2. Okay, CS2 is present in our full equation up here, okay, as one of the products. It's also down here. Okay, so now, if we take that we have 0.005 moles of this C3N4, it's in a 1:1 ratio with CS2. So if we have 0.005 moles of C3N4, we also have 0.005 moles of CS2. We're going to say as well that down here we also have 0.005 moles of CS2. Right. Right, and we see that they react with 3 moles of oxygen, so 3 times the amount of moles of oxygen. So that means we have 3 times 0.005, so that's going to be 0.015 moles of oxygen. So that's the number of moles we have. To find the litres that we need, it's going to be 0.015 multiplied by 22.4 litres, and that gives us an answer of 0.336 litres. Okay, that's part 2. Part 3 then, what is the number of mercury atoms produced? Alright, so we have 0.01 moles of mercury. To find the number of atoms, we just multiply that by Avogadro's number, so it's going to be 0.01 multiplied by 6 by 10 to the power of 23, and that gives us an answer of 6 by 10 to the power of 21 atoms of mercury. Now, part 4, which perhaps is the most difficult part. Alright. Okay, so what is the total number of moles of gas formed? So what we're actually going to do here is I'm going to cut this out. Okay, I'm going to paste it down here. Now, okay, so we're looking at the amount of gaseous product that we formed in these reactions. So that means we're looking at the amount of SO2 that we created, the amount of carbon dioxide we created, the amount of SO2 we created, because that's all gaseous, CN2 and N2. Alright, so we're looking for the amount of each of those that we have produced in moles. Okay, so it's working with the information that we already have using our ratios and so on. Okay, so here our number of moles, everything here is in a 1:1 ratio, and the amount of moles we have of everything here is actually 0.01. So here we produce 0.01 moles of SO2. Okay, for this then, CO2 and SO2, alright, we have we looked at earlier in our question that we had 0.005 moles of this CS2, 0.015 moles of oxygen, but the CS2 is easier to use because it's it's one of them rather than 3. Okay, so that means we also have, seeing as it's in a 1:1 ratio, we have 0.005 CO2, plus we also have 2 SO2, so that's going to be twice 0.005, so it's going to be 0.01 moles of SO2. Okay, so that's a gaseous product there. Here then, we learned earlier that we have 0.005 moles of this C3N4. Okay, now it might be a little bit confusing because up here in the maybe the original equation, we had that C3N4 was just singular, was just one C3N4, and that was worth 0.005 moles. Down here it's the exact same. Okay, so even though it has 2, we still only have 0.05 moles of it. What this is meaning is that that is twice the number of moles of nitrogen that you have. Okay, or it's in a ratio of 2:3:1 across. Okay, it's not necessarily that the number of moles itself is changing, but the ratio between what is being created here in this decomposition, it's the ratio that's being changed rather than the actual number of moles. Okay, if any of you have any difficulty, please message me, because hopefully I've explained that there, but if not, just ask for another explanation. But it's the ratio that's changing rather than the actual number of moles. Okay, so up above it was in a different equation, so there was different ratios involved. Okay, so we still have 0.005 moles of that C3N4. Okay, okay, and that creates then, using our ratios, you're able to calculate. Okay, so that means we have, of our nitrogen, we have half of that, half of the 0.005, so we have 0.025 moles of N2, and we have then 0.0075 of our CN2. Okay, so all we have to do then, we have found a number of moles of each of our gaseous products. We just have to add them up. So it's just 0.1 plus 0.005 plus 0.01 plus 0.0075 plus 0.0025, and that gives us a final answer of 0.035.